Yeah, hi again. Can you see my first slide?
The most spoken sentence in this year. Can you see my slides? The answer is yes.
Yeah, exactly. Can you see my second slide now? Okay, great, yeah. Thanks. And everything is working as both. Yeah, exactly. Jens kind of already gave away what I'm going to talk about today. I'm going to talk about the classical shadow formalism broadly. And this is not a new idea. It's like just a kind of a way how to formalize ideas that date back to like 2013 and of course to a certain Jens Eisert. But I think like we still added something to that story by like providing a rigorous framework about how to reason about the randomized measurement paradigm. Classical shadows are a variant of randomized measurements, and kind of how to use rigorous probability theory to kind of derive error bounds for kind of quantum information extraction based on randomized measurements. And in the end, like on a very, very high level, you should view this as a very efficient quantum to classical information converter. A bit like you might be familiar with analog to digital converters that allow you kind of to like wire an analog device to a digital device like a computer. And like our vision is to kind of use this classical shadows framework or more generally randomized measurements to make very, very efficient interfaces between a quantum computing device and a classical processor. And I will try first in my talk to like kind of motivate why we need that actually, why a quantum to classical converter might be important already now in the NISQ era. And then like I will introduce the formalism, and then later on I will tell you a bit about what you can do. Because suppose that you have access to an efficient quantum to classical converter, then you can start like playing around with cool things. Like kind of take a NISQ device on one hand side and a powerful classical computer on the other hand side that runs some machine learning algorithm. And we will see that this is surprisingly powerful, maybe more powerful than one might have anticipated originally. But I want to more give an overview over these things, and then we can discuss in detail later. Okay, and again, please interrupt me at any time if you feel like having a question. And so the outline, before I start, I want to like emphasize that kind of, I already said that kind of many of these ideas are not new. The results I'm going to talk about are roughly from 2020 and 2021. They are new, but the ideas date back rather long. For instance, I myself have been thinking about these kinds of problems since I started my PhD in Freiburg, but the results I'm going to present today wouldn't have been possible without my two amazing co-workers. I guess most of you know one of them, John Preskill, my boss at Caltech. But the other one, I also want to make you aware of Robert Kueng, who is a very, very talented PhD student in John Preskill's group. And he's really amazing. And he did a lot of the theory contributions to our works, but also all of the numerics. So he's kind of really good. And best of all, he's also a very nice guy. So kind of keep him on the radar. And with that, I want to like move on to my outline. I want to first start by motivating the need for an efficient quantum to classical converter by revisiting VQE, variational quantum eigensolvers, which are kind of like very prominent these days. And this will kind of tell us that in order to actually kind of run them as efficiently as we should run them, we actually need a way to like read out certain quantum information very efficiently. And this will pilot us right into more interesting territory, namely the randomized measurement toolbox, which is one way to achieve this goal. And more precisely, the classical shadows formalism, which is just a rigorous way of how to reason about these things. And then I will talk a bit about like the applications of classical shadows per se, before switching gears a bit and then really talking about how you can combine ideas from classical machine learning with classical shadows to come up with surprisingly powerful learning techniques that are empowered by quantum data. So kind of classical machine learning empowered by quantum data. And then I will wrap up and we will have a conclusion and then we can discuss whatever we want, okay? So kind of the motivation for a quantum to classical converter for me is the Vqa Readout Problem. So kind of VQE is short for variational quantum eigensolver. And this is kind of an idea that is usually attributed to Feynman, who kind of famously said that microscopic systems are not classical, they are quantum. And so we should use quantum processing devices in order to simulate them not classical processing devices. And it's also customary to have a picture of Richard Feynman on this slide, but I guess all of you know how Richard Feynman looks like. I guess not all of you might know that Richard Feynman used his Nobel Prize money to buy a beach house in Mexico. And I guess even fewer of you know that you can rent that on Airbnb. That's actually a really good idea. If you ever happen to be like kind of in North Mexico, like South California, just try to do that. It's actually kind of worthwhile. Okay, but back to physics and VQE. The idea is to kind of use quantum architectures like the NISQ devices we have today in order to simulate other quantum systems that we are actually interested in. And the paradigmatic example for that is the electronic structure problem, where you have a not entirely small, but also not too big molecule, and you're interested in its exact molecular quantum mechanical ground state energy. And then this is kind of a difficult problem, but the idea of VQE is to kind of first encode this problem, like the electronic structure problem, find the ground state of a molecule, into the lowest eigenvalue of a synthetic Hamiltonian that doesn't describe the molecule anymore, but it describes kind of an n-qubit system. So kind of we go away from the molecule and the quantum mechanical nature of it, but we use some encoding, like a Jordan-Wigner transform, in order to map it, the energy function, to a synthetic Hamiltonian on an m-qubit device. And then on this m-qubit device, we can try to run the variational principle, because the lowest energy of a Hamiltonian is not a difficult problem in linear algebra. It's just like kind of the smallest eigenvalue. And the variational principle, the Rayleigh-Ritz principle, is just like kind of try to find that. The problem becomes difficult because the Hamiltonians are huge. It's a curse of dimensionality problem. And the idea, the difficult part, is actually kind of to come up with an ansatz function for your variational parameter, for your variational ansatz function, which is kind of a big quantum state that is kind of parameterized by certain parameters. And then you have to like kind of read out the associated synthetic energy function. And that happens in an exponentially large space, because if you have m qubits, you need 2 to the m classical parameters to describe the thing. And the idea is kind of to outsource this difficult part, the part of evaluating the synthetic energy, onto a not too large quantum platform, like a NISQ device. Suppose you had access to like kind of a small quantum architecture where you have m qubits, and you can do certain circuits. Then you can like kind of parameterize these circuits by classical parameters and get a family of variational ansatz functions. You vary the circuits, you will get different states. And then the idea is kind of like to use this quantum device as a coprocessor that kind of computes the current synthetic Hamiltonian expectation value at your current state, at your current, where you currently are. And then you kind of read that out and a bit more, and then you kind of make a classical stochastic optimization for the parameters that describe your variational circuit, and that way you try to heuristically find the ground state energy. Now, this is kind of a compelling idea. It's very popular these days. It seems to work. Of course, it's not without problems. This is a heuristics. It's not clear if it always works. But I don't want to focus on like the fundamental VQE problem here. I kind of want to focus on a problem that is often overlooked, which is what I call the Vqa Readout Problem. Kind of if you want to use a quantum device as a coprocessor to efficiently kind of estimate energy functions achieved by your current variational state, then the least you have to do is to kind of estimate this synthetic energy function, right? And so kind of we have to get classical information in like the simplest case, just a single number, but we have to extract classical information from our quantum coprocessor. And that's not as easy as you might think it is, because the first problem is when we do the encoding of the original problem, like a Jordan-Wigner transform, for instance, then the Hamiltonian on our coprocessor is not native. It's not a natural Hamiltonian for the m-qubit system, it's a synthetic one. And so it's typically comprised of simple terms like Pauli observables, but there's polynomially many of them. And if you want to like kind of estimate the synthetic energy, you might have to like estimate polynomially many Pauli observables. And the second problem is, as you all know, in quantum mechanics, measurements are destructive and probabilistic. So in order to just estimate one of these terms, you have to do actually many repetitions in order to get sufficient data from your single shot measurements so that the errors average out. And so actually just getting a classical representation of a single number out here is not as easy as you think.
Of course. But I mean, of course, you can recycle some parts, right? I mean, you don't have to do the full preparation for each measurement, but that goes.
Sure, I agree. But it turns out that if you talk to practitioners, that's actually one of the main bottlenecks they have. Mm-hmm. And like the example I want to pick is a beautiful Nature paper by the Blood group in Innsbruck, where they kind of try to do VQE to simulate an interesting one-dimensional field theory, the lattice-Schwinger model. And kind of, it's not a naive VQE protocol, but it has like a nice twist, because the goal they have is to prepare low energy eigenstates of the lattice Schwinger model. So they're interested more in eigenstates, not only the ground state energy, and also not only the ground state, but a kind of low energy eigenstate, also the first excited state. And in order to achieve that, they kind of had a cute trick, because kind of first they take the lattice Schwinger model and they use a certain encoding to map it on qubit Hamiltonians. They use Kogut-Susskind encoding, I think. And then in the end, they end up kind of with a two local Hamiltonian on n qubits that has that number on the number of terms is roughly quadratic in the number of qubits. That's kind of the energy functional for their lattice Schwinger model. But remember, they're not simply interested in the ground state energy, but they're interested in low energy eigenstates. And now you can quickly convince yourself that a pure state, if you restrict your attention to pure states, then a pure state is an eigenstate of a Hamiltonian if and only if the variance associated with the Hamiltonian vanishes. And so rather than minimizing the Hamiltonian itself, they minimized the square, the variance of the Hamiltonian. And this produces, in their case, an effective sum of four local terms with m⁴ Pauli terms. That's kind of what they had to do in order to get the lowest energy ground states. And so you can see that the Bqe readout problem starts to matter here, because they have to estimate m⁴ different terms, and each of them sufficiently accurately. And this is only a polynomial factor, but it is a polynomial factor that starts to hurt. And I talked a couple of weeks ago, I talked to the first author of this paper, Richard Kueng, and he really confirmed to me that it was this readout gap that kind of limited the scope of the experiment. So in the end, they did a proof of principle for 20 ions, and they ran the actual VQE algorithm for only 8 ions. And the reason was that this readout procedure that you have to do in every iteration of a VQE algorithm just took too long. They were very confident to put more ions in that time. But it was really this Vqa readout problem that kind of limited the scope of this particular paper. And if you kind of look at
a quick question, but
yes,
by the readout problem here, you mean practically hard, not complexity theoretically hard?
No, it's all polynomial here.
Yeah, exactly. Okay.
Kind of like, yeah, it's
practically like okay, yeah.
Like, I don't know, do you like SDPs? I personally love SDPs, and I always say they're kind of efficient, but they're only efficient theoretically, right? Like kind of the runtime of an SDP is also of the order m⁴. And with general purpose solvers, this gets you pretty quickly.
Totally. To add inside to Indri, I mean, that's a trapped ion system, right? But I mean, if you talk to cold atoms people, I mean, it took like 30 seconds per shot. And then polynomial scaling gets a different flavor once you have to wait 30 seconds to get a single beep. And then you want to get statistics for an expectation value. I mean, good luck. This takes long.
Exactly, but bottom line, Alex, you're right. This is not really a complexity theoretic obstacle. It's just like kind of a polynomial factor that starts to hurt if you actually want to run the iterative algorithm.
Thank you.
Very good, thanks.
I think I missed something. You were saying they minimize the variance.
Yes.
Why is it that it ends up with low energy eigenstates and not any other ones, high energy?
That's
ones?
a very good point. Of course, they have to like kind of start the ansatz state kind of smartly.
Oh, okay. So they build that into the ansatz somehow. Okay.
It's not completely straightforward. Okay. Because if you're perfectly right. If you just minimize the variance, you will get any eigenstate. And so you have to like play around with your starting ansatz function.
Okay. Mm-hmm.
Can I ask a question to your plots?
Yes.
The Bonnet-Mon-Roche one,
yes.
like the brown one.
Yes.
Where is that in the plot?
On the left-hand side?
On the right-hand side.
Where this is?
Yeah. Is that it? Like, is that the brown one or the one that says Google? I'm a bit confused. That's why.
Yeah. That's this line.
Okay.
It's kind of this partial tomography results that those people had.
Yes.
With Google.
Yeah.
Yes, it's the brown line here.
Okay. Thanks.
But yeah, that's just kind of a visualization of a kind of like how the cost, like the total number of experiments, of experimental repetitions you need in order to extract one of these energy values scales with system size. And you can see that kind of the naive method, which really involves m⁴ measurements, kind of like scales on this logarithmic plot, really unfavorable. And you can also see that actually kind of like the Innsbruck gang wasn't stupid. Kind of they had very good theoreticians who came up with a handcrafted method that scaled much, much nicer. It's this blue line. But even this handcrafted method only got them to 20 qubits. And today in this talk, I want to talk about randomized measurements, which achieve the red and orange lines here. And in particular, what you should see here already is that kind of the scaling with system size is very, very benign. I mean, these curves grow, but they don't grow quickly.
Can I ask?
Yes.
So you said that's the number of measurements or experiments that you need to get one estimate, but does that mean you need that many experiments to get one estimate up to like chemical precision?
Yeah, exactly. Up to like a certain accuracy that is good enough to drive the update rule.
Okay, I see. Thanks.
Okay, and remember, this is like a hybrid quantum classical algorithm, so it involves many steps, and each step requires you to do one of these. Okay, but very
short
good.
question, Richard.
Yes.
So, but the scaling in the precision is still 1 over, I think, epsilon squared.
Epsilon squared, yes. Yes.
Okay, so this is basically the constant in front of it that you picked here, more or less.
Very good. Very good observation, thanks. Okay. So that's kind of the motivation part. And now let's dive in a bit deeper and see how we can get kind of like readout procedures that only scale very, very mildly in the number of qubits. Okay. And that's kind of where classical shadows and more generally randomized measurements come in. And the problem I want to like focus on for this middle and central part of the talk is exactly the Bqe readout problem, just phrased a bit more generally. How do we efficiently estimate many structured observables? And I want to make it a bit simpler, just like for illustrative purposes. Let's assume that we want to estimate many terms, like the individual terms in a Hamiltonian, but each of them is somehow nice and structured. Like for instance, it's a Pauli observable, and let's even assume that it's low weight, which is often the case in Bqe approximations. Okay.
And low weight, we mean constant weight. Well, whatever that
yeah, just a fixed number. Let's think of it constant, but like your Pauli observables better have like a lot of identity terms, like a Hamiltonian has.
Like 3.
Okay. And the ansatz, and of course, this is like many good ideas. It's not my idea, but it's, I think, one of Jens's, is based on the infinite monkey theorem, which I really love. And the overall idea is to like forget about the fine structure of the terms, just sample yourself Pauli measurements uniformly at random. Kind of, we want to estimate many Pauli observables, and we get to choose which kind of Pauli basis we measure for each qubit, because that's maybe the number of the kind of measurements we can do. Then just stop worrying and just roll dices. And why could this be a good idea? And there's actually like a very good intuitive explanation of that I took from a recent paper by Steve Lamia. And it's really based on the infinite monkey theorem. Suppose that we are interested in kind of predicting an arbitrary low weight Pauli observable that I try to visualize here by this bar. And like the white bars mean that it's identity there. And because it's identity there, it doesn't matter what we measure. What really matters here is that we have kind of maybe 2 Pauli X terms next to each other. And if we now kind of just randomly assign Pauli measurements for each qubit, we are completely free to do whatever we want on like everything that is white on the left-hand side. The only thing that matters is that where the Pauli observable is non-trivial, we have to hit the same we have to do the same Pauli measurement. Otherwise, we don't get any meaningful information about the statistics. Okay. And now you can probably start to see why like random sampling is not a bad idea, because the probability of hitting such a low weight Pauli string is exponentially small, but it's exponentially small in the weight of the Pauli. It's not exponentially small in the number of qubits. Okay. So that's kind of pretty cool already. And of course, if you think about single shot measurements, which we have in this example, we need multiple repetitions of Pauli terms in order to get sufficient statistics. And so there will be an oversampling factor. So we roughly expect 3 to the weight over desired accuracy squared random measurements. If we do that many, then we expect that we have sufficient data in order to epsilon accurately estimate a single low weight Pauli observable. That's just elementary statistics. Okay. But now comes the cool part. because everything is random, we can effectively do a union bound over estimating a lot of low-weight Pauli observables at the same time. And as most of you know, union bounds kind of scale logarithmically in the number of terms. And so if you kind of like randomly sample each of your Pauli measurements, then the number of total measurements you expect to need in order to predict L low-weight observables up to accuracy E epsilon each is only logarithmic in the total number of terms because of a union bound. And this is essentially what we saw on the last slide. It's like kind of very small increase in system size for our plots was a log of the number of qubits. Okay.
So can I just start? I don't think I quite get this intuition. So your color coding in your figure, is that meant to be Clifford operations, or are you thinking of some rotation?
Just single qubit rotations. Like the rule of the game.
Surely the probability is just 0 because you're not going to get the right rotations, right? Like you'll
yeah, no. I won't get the right rotations most of the time. But if kind of my target is identity almost everywhere, except for 2 sites, for instance, and I get to like choose single qubit Pauli measurements at random, then with probability 3 to the -2 in this case, 1/9, I will hit both of them and I will get meaningful information. I agree, that's a small number, but it's exponentially small in the weight of the observable, not the number of qubits.
Do I get right? Like the color code also means it's not any rotation, but it's like sigma z, sigma x.
Yes, exactly. Sorry. Yes, I should be clear.
Also, I think Austin thinks of like continuous rotations.
Yes.
Yes, that's what I'm thinking of. Yeah.
Thanks. Do Paulis. Do just do Paulis. Do just do single qubit Cliffords.
So every time you want to measure something like, I don't know, say the red things are ZZ, right? So every time you want to measure some ZZ Pauli term,
yes,
instead of measuring the ZZ term, you measure the ZZ term and a bunch of other stuff, right?
Yes.
And sometimes even, I mean, experimentally, don't you expect that to like increase the measurement errors? I mean, you need to open up your system more, you need to introduce more couplings and so on, isn't that going to
I don't expect this to introduce actually kind of, as long as you can, I have to assume that you can do single qubit rotations with very high control, single qubit Cliffords. But I think that's a reasonable assumption, even for current devices. But exactly kind of the thing is that because we don't only measure these things, but we do something randomly everywhere else as well, when another term comes that might have a support on the first 2 qubits only, we also have a chance of hitting that.
Right. Okay.
And that's kind of the intuition, at least. And this intuition is not new. And kind of what we provided is actually kind of a rigorous and powerful generalization of this idea. Like a formalism that allows you to explicitly reason about these kinds of ideas with explicit, rigorous error bounds, not only like kind of approximate statements like this. And also kind of, it's in a way independent of the measurements you actually do. Like this example is based on single qubit Pauli measurements, but you could consider different ensembles of measurements. Okay, so let's do it a bit more formally. Kind of like when we came up with classical shadows, we kind of envisioned the following randomized measurement procedure, just an abstraction of what we did on the last slide. We have like a state rho, an unknown n qubit state. Let's focus on n qubits. And then what we can do is we can do a certain random unitary rotation. In the example before, it was independent single qubit Clifford rotations, followed by a computational basis measurements. Okay, and so kind of every time we can press a button, we prepare the state like a variational ansatz state. We can sample a random unitary transformation, and then we do a computational basis measurement, and we will get out a bit stream. And then it's interesting to kind of actually view this with some tricks as a quantum to classical channel. Like suppose kind of on the left-hand side, we have the state, and this entire procedure, if we kind of ket-bra the outcome, if like kind of B hat is the computational basis state we kind of obtain, we can ket-bra that, then it's kind of a quantum state, a pure quantum state, a computational basis state. And we also should maybe remember that we kind of did a unitary basis transformation for our computational basis. And so we probably should undo that on the output. But kind of this is a meaningful.
Sorry, Richard?
Yes.
So you're saying that you're applying the random unitary? Do you mean Haar random unitary? And
no, this is kind of the formalism works for any unitary almost, for any ensemble.
So you don't need to implement random unitary. It's just unitary from some set.
All I'm saying is kind of if you kind of view this entire process as a channel that takes rho and maps it to kind of computational basis outcome we had and the inverse unitary transformation we did, then this is a quantum channel. And on average, at least, kind of, right? You have to average over everything. You have to average over your random unitary sampling. And now, Maria, that depends on the kind of ensemble you choose. And you have to average over the computational basis outcomes, which are defined by Bohn's rule. And then you get something that looks a bit scary, but it's actually not as scary as you think. It's kind of linear in the state rho, and it's a nice quantum channel.
And now, in a second, say what you require of the second, right?
Yes. Maybe not in a second. In a second, I will say something vague about that. But those of you who are experts, there's a unitary, as an adjoint action of the unitary here, and then an adjoint action of the unitary here. So two adjoint actions of a unitary. And now I'm claiming
this is like forgetting about the measurement result, though.
No, it's kind of taking the measurement result, turning it into
summing over it, right?
Yes, exactly.
Sum over it.
Yes.
So that way the output state after the map M is where you forgot about what the outcomes of the B's were.
Yes, exactly.
Okay.
That's kind of like what I would get on average if I kind of like empirically average all of these outcomes after many repetitions.
Okay.
Okay.
Mm-hmm.
And there's a closed form expression here, and sorry, there's like one expectation value to value, and it involves an integral over the ensemble we chose, and it involves 4 unitaries. 2 times u dagger. And now one observation that is not very surprising when you think about it is kind of if the ensemble is nice, for instance, as Maria suggested, Haar random, then we can efficiently compute this guy. Because on the right-hand side, what you see here is effectively a Turing formula. That kind of first page of every randomized benchmarking paper. And so if U is nice, and I don't want to specify like kind of what nice means, I will do that on the next slide, you can efficiently compute this average channel. Okay? And once you can compute it, you can classically invert it. Like we know that for quantum channels, it's impossible to invert them in general. But here, this is already kind of on the classical side. This is just classical post-processing. We take the bit string we measured, we remember the unitary transformation, and then we can form this guy on our classical hard drive. And on this classical hard drive, we can effectively invert this average map and apply it to kind of the single shot measurement outcome that we stored in this fashion.
But this won't apply to Haar random.
It will.
No, because if it's Haar random, you'll just have uniform noise.
No.
And that can't be inverted.
No, you don't have uniform noise. Remember, there's like 4 of these unitaries.
Yeah, I mean,
structure. You're not just twirling the whole thing. It's structured.
Yeah. I mean, he's not averaging. He's not measuring the average state. He's picking just sampling unitary, measuring while still knowing the unitary, right? and then inverting.
Exactly, you remember the measurement basis and undo it here.
So the equation on the last line isn't strictly what you mean.
Oh, it is.
Because the M will depend on B, won't it?
No, it won't, because I average out B and U. But there's a typo, like the dagger should be on this side.
Yeah, no, that's okay. Okay, all right.
You forgive me.
All right.
And a naive question.
Yes.
How can M be efficiently computed if already the read-in of rho is inefficient?
What do you mean read-in? This depends a lot on when U is nice. Like
but reading in rho is an exponentially large vector, right?
Yeah, we never read in rho. That's just a single shot experiment. That's the idea.
Okay.
The quantum computer is doing that for you.
Okay.
Yeah, but I mean, don't you need like crazy many samples?
No, that's the next the slide after the next one.
Okay.
Okay. But yeah, you're asking all the right questions.
Yeah,
but here this is just kind of like a description of a single short experimental run that a person with access to a NIST device could do. You prepare a state that you care about. You do a random unitary transformation, provided that it's kind of efficiently tractable, and then you do a computational basis measurement. And the rest is like kind of just massaging the classical outputs and just viewing them as quantum states. Okay. And just to make it a bit more concrete, if like you would actually be Haar random, then this twirling formula would give you a depolarizing channel. And it's easy to invert depolarizing channels on your classical device. And if you actually do that, you kind of take the output, the single shot output of your measurement, computational basis state plus basis rotation, and then you can apply the inverse of that channel efficiently on your classical computer. And what you will get is kind of a sketch, a snapshot of the actual underlying state that is constructed precisely to ensure that on average, over the classical randomness that we insert by using a random basis measurement and Born's rule randomness over the outcome, if we average over all that, then this classical sketch will be exactly the underlying state row.
Yeah, I actually have a question. So yeah, I aware that M inverse can be efficiently computed in sleep, but is that also true for UB?
We'll talk about specific examples of that.
Okay, yeah.
Kind of like it has to be
just to clarify, your example is exactly the model I was having in my head. You have a completely depolarizing channel.
Yes.
You have rho comes in,
yes.
The channel destroys all the interference terms.
But it's not a completely depolarizing channel. It's not mapping you to the maximally mixed state, but there's a bit of the state surviving.
Yeah, I mean,
so that comes into the niceness, does it?
Yes.
So is it correct to say that you're not twirling the state, you're twirling the POVM?
Kind of, yes. I'm twirling this quantum to classical channel.
Yes, that's yeah.
I'm twirling neither the state nor the POVM, but a combination of both.
I mean, Jonathan, I think one way to read this is that like the UB together can be just regarded as a big POVM, and this is a frame which you can then invert because it's overcomplete, and it's like nicely structured overcomplete because it just arises from orbits of basises. So therefore, like the inversion of the frame operator is just like a dimensional factor which bothers Austin, which comes in.
Yeah, and it should bother all of us, but there's another trick coming down the line.
Yeah.
Okay, but this is kind of just one way of like taking a single shot quantum measurement by injecting additional classical randomness and kind of using it to construct what a statistician would call an unbiased estimator, like a random matrix that in expectation over all degrees of randomness actually exactly reproduces the underlying state. Okay. And with that, we are actually basically in business because a single instance of this random matrix is going to be a terrible estimator. But if we start forming empirical averages, if we kind of repeat this procedure multiple times, each time choosing a new random unitary, then we get independent snapshots. And if we kind of start to like averaging those, we will get more accurate and more accurate approximations of the underlying quantum state without ever having to read it in. Okay.
By the way, of course, I'm familiar of the theory behind anyway, but I'm not so sure whether you could use the same circuit many times. Would that work? I mean, do you really have to pick a new circuit in each run?
I think the theory is nicest there and potentially also strongest. Mm-hmm. That's a very good question. I would like to like defer that to later because I have an opinion. But the answer to that question, I think, is not easy.
Okay. Yeah, sure. I mean, it reminds me of the compressed sensing basis problem, somehow a bit of that type, because you look at lots of dependencies you openly hate in this context. Sure.
Okay. But now we are basically in business. Remember that we're interested in predicting like many properties of an unknown quantum state row. And now we kind of know how to do that. We form these snapshots. For each snapshot, we can kind of compute the observable we care about, and then we just empirically average. And statistics and probability theory tell us that if we kind of empirically average random variables, they kind of then they converge to the expectation value, and the expectation value is exactly the observable we want to know. The only remaining question is like kind of how fast do you converge to this desired expectation value? And this is kind of the main result of our work on classical shadows, our first work. And basically what we show is that the number of snapshots we need, the number of single shot measurements you need, actually scales logarithmically in the number of terms we have to predict, inverse quadratically in the desired target accuracy. And it also features an additional kind of norm factor that takes into account the type of observables you want to predict. And we call this the shadow norm. And this kind of additional expression depends on the measurement ensemble. And this shouldn't come as a surprise, because if you kind of want to control how quickly a sum of independent IID random variables converges to its expectation value, which is kind of the thing we're looking for, this is our estimator, then the convergence speed is controlled by the variance of my random variables. And the variance of kind of these guys depend on the observable in question. And it turns out that they kind of define a norm. And here, now I want to become a bit more concrete. So far, like everything I said is fully general. It's kind of valid for almost every kind of unitary ensemble. But the most interesting ones are ones that are very structured. And one of them are like kind of building on Maria's intuition, m-cubic Clifford rotations. That's kind of like an approximation of Haar random unitaries that are actually tractable, at least in theory, because they're only polynomial size. They are so-called unitary 3 designs, which means that they reproduce the moments of the Haar measure up to third moments. And in order to make our twirling formula work from the last slide, you only need 2. And what you can show there is actually exactly kind of this twirling formula here becomes exactly a single depolarizing channel, but it's not completely depolarizing. And the representation you get here is also efficient because kind of each measurement outcome is a stabilizer state, Clifford applied to a computational basis state. And the inverse of a depolarizing channel, you don't have to carry that out. It's kind of just a combination of like scaling your stabilizer state and subtracting an identity contribution. But kind of what you get here is an efficient representation of each of your snapshots. And this mysterious shadow norm is actually nothing but the Hilbert-Schmidt norm of the observable. And so if you just look at this number, then you see that as soon as the Hilbert-Schmidt norm squared of the observables we care about that is small, constant ideally, then we can predict a lot of them with very few measurements. And the prime application for that are entanglement witnesses, or more generally, fidelities with respect to pure states. Because if you're interested in predicting many fidelities with respect to pure states, each of your OLs would be a pure state, a projector onto a pure state. Hilbert-Schmidt norm is 1. And that means that log L over epsilon squared, many independent repetitions, allow you to predict a lot of fidelities at once. And there's no dependence on the ambient dimension whatsoever. And this plot kind of highlights this, because here we just kind of checked how many measurements do we need in order to like accurately compute fidelity of a hypothetical underlying GHZ state with respect to the GHZ state up to 99 fidelity. And you can see that kind of the classical shadow formalism is completely independent of dimension. This on the x-axis we label the number. We let the number of qubits grow from 0 to 120.
Is it really completely flat? Sorry.
Maybe I'll go quickly. So, I mean, basically, what you want in this theorem, what you want is the expectation values of rho with respect to these OLs, which are the operators you're trying to estimate. And now what you say is that you construct this classical shadow, this rho hat, and then if you construct the expectation values with respect to this classical shadow, then they're all close for everything you care about. What's confusing me though is that this rho hat is some classical object that you get by applying the inverted channel to the outcome of your measurement and this like adjoint action of the unitary. But how can you do that efficiently classically? I mean, the unitary is 2 to the power of n and the number of qubits. I mean, what is this actual rho hat object? Like, how do you store it?
Yeah, that depends on the measurement ensemble. Very good question. I was a bit too general on the last slide because I tried to emphasize that the formalism is general. It's not clear that you can implement it efficiently. Here we have an example where you can implement it efficiently, because each unitary U is a Clifford unitary. And Gottesman-Nil allows you to like kind of treat that efficiently. Right?
Okay.
This is a computational basis state by construction. You apply a Clifford unitary to it. You can store that efficiently. And the inversion formula, because Clifford unitaries are unitary 2 design, is effectively inverting a depolarizing channel, which is just a rescaling and subtraction of the identity map.
Okay, so the answer to the question is that this like row hat object, the actual way you store it, the representation of this object, depends on like what representation you have available to you for your unitary matrices.
Yes, exactly.
Okay.
And if they are nice, that's what I meant, then like everything works out. And here's also like kind of empirical proof. We managed to go up to 120 qubits here. That's no joke.
Got it. Thank you.
Two things. So the first question, just to clarify, Richard, when you say you estimate a lot of fidelities of observables, this is kind of like in L infinity norm.
Yes.
Like every one of them. Yes. Okay. I'm just that I don't.
And that's exactly, Ingo, how you bypass these no-go theorems from quantum state tomography. Because kind of what you get if you were like to do full state tomography is you get kind of like.
I mean, as you know, I mean, we had like these old notes like about estimating like average fidelity simultaneously, and yeah, I think you can go about this. I mean, if in addition you know that like the fidelities you're estimating, for example, are stabilizer states which are randomly drawn from the Clifford group, then you can actually concentrate also in L2 norm instead of L infinity norm, because you can then use like shadow vector, a median of means for vectors or something like this, and the overall variance. So I think there's something, but this is not yet in there. So this is really L infinity. Okay, and the other things, I mean, you know, said that like if the unitaries have an efficient representation, then you're fine. But this is not entirely true, because you also have to. I mean, also the observable has to have no compatible efficient representation. Or I mean, this is really here it's stabilizer states and Cliffords. So you're really talking about something which you can kind of efficiently estimate the entire thing.
Yeah, very, very good observation. Okay. Thanks. That's very important.
So another question. So when you apply random Cliffords in this for this U that you just shown, you're basically sampling over the expectation values of random Pauli words.
Yes.
That like in your motivation you were talking about Vqe, where you only want to actually measures expectation values of the terms that are in the Hamiltonians that you look at. So isn't this sort of overkill, or do you have a way to constrain?
Yeah, that's why we have a second application. The left-hand side, where we talked about, are global Clifford unitaries. In particular, they have entangling gates and they are long circuits. In the introduction, I was talking about random single qubit Cliffords, which is a different ensemble. It's a tensor product of single qubit Cliffords. And then like the story also works out, but it looks a bit differently. Kind of here, if you have like M single qubit Clifford rotations, then it's nice because kind of everything factorizes into tensor products here, because you have a computational basis state, which is a tensor product, and you kind of apply tensor products of single qubit unitaries. So your classical shadows are actually elementary tensor products. This is why you can efficiently store and manipulate them. And the inversion formula is also not so difficult, because everything decouples again, because here you are kind of an elementary tensor product, and you have like a tensor product of single qubit depolarizing channels, which you can also efficiently invert. And the interesting thing is like, what about the variance term? What about the shadow norm? And you can actually prove that the shadow norm scales exponentially in the weight of the observable. 4 to the weight if you have a general observable. And if you have Pauli observables, it would be 3 to the weight. And that's a rigorous proof for the intuition we had before.
I have one more quick question.
Yes.
You didn't mention it, but you write that median of means estimation is required.
Yes.
And I have 2 questions. The first one is, how can you ensure that like the setting allows you to gain any benefit from using median of means? And where does it precisely come in?
Very good question. Rather technical. It comes in before I got a question by, I forgot the name, but somebody of you was rightfully worried about like kind of this being a depolarizing channel that is kind of very close to the maximally mixed state. And if you start inverting it, you have to like scale it up exponentially largely. Okay. And that's kind of the problem that happens if this kind of inverse has exponentially large coefficients in front. And then weird things can happen because kind of like you start averaging random variables that are with very, very high probability small and close to expectation value. But with some small probability, they can be ginormous. And so you have to start worrying about outlier corruption. And median of means is a simple, well-understood technique to remove outlier corruption danger, because the median is stable with respect to outliers.
Okay, thanks.
And like mathematically, if you don't use median of means, you wouldn't get the logarithmic factor in a number of terms.
Can I ask one more question?
Sure.
Can you go back one slide? So basically, you have this this fact that if you construct the shadow rho hat, then you get that the expectation value of rho hat is equal to rho. And
yes.
So does this hold for all states rho?
Yes.
Okay, but okay, that seems kind of surprising. So I mean, there has to be some sort of kind of sufficiently complicated condition on the U in order for this to hold.
Yes, it has to implement a tomographically complete measurement if you kind of take all possible instances into account.
Okay.
Or this being a 3 design.
Yes. But you don't need single qubit 3 design is enough, right? So it's like not as strong as you think.
Good.
But yeah, your estimation procedure, if you kind of like look at all options, you can't have any blind spots. You're right, Ryan. That's important. But that's actually kind of not such a hard restriction. And kind of in a way, you can view this randomized choice here as implementing a very large POVM, but you never kind of measure everything because the number of samples you need is so small that you're kind of done pretty quickly. Okay, so that's kind of like our main result from roughly 1 year ago. And since then, a lot happened. And what was really...
Maybe I can still interrupt you again.
Sure.
What happens if you don't do single qubit Cliffords, but single qubit random?
I guess empirically, you would do better because you get slightly better concentration, but I think it's comparable. The theory wouldn't change at all because kind of when you compute the variance, you actually only need 3 moments, and the Cliffords are a 3 design. But your storage will also kind of marginally increase, right? But I would say the two are very comparable.
Thanks.
Okay, but like a lot really has happened in the last year, and that kind of made me really happy because like most of the smartest contributions here are not by me or my co-authors. So like kind of really the community took over and a couple of smart people contributed smart results here. The first one, and that is kind of like an obvious one for a theorist, is kind of like Struchalin et al. Did an experimental implementation of actually kind of the global Clifford rotations, and they kind of showed that it really outperforms maximum likelihood in the low sampling regime. Then I also started teaming up with the folks in Innsbruck, where we started like to extend this formalism to also predict polynomials. Kind of like once you have the formalism in place, it's actually not that difficult because you can write a quadratic polynomial, for instance, as a linear function on a tensor product. And then you just start replacing the tensor products by independent shadows. And then you average over it, and then everything kind of works out as you expect. And this allows you to like probe entanglement more efficiently in many body systems. And we did that with Innsbruck data also. And then some folks in the US kind of established noise robustness, kind of like what happens if you don't have full perfect control over the unitaries you implement, then you have slight offsets and the inversion will be slightly wrong, but it turns out that this is also stable. And I think this is a substantial generalization by Steve Lamere and friends. Steve Lamere actually saw that the entire procedure, the core of the argument here, is invariant under twirling, and another twirling formula at the very beginning and at the very end, basically because we sample unitaries at random.
Yeah, I mean,
and so you can twirl over the noise in your measurement and use a randomized benchmarking procedure to calibrate all the parameters you need to actually kind of adjust the inversion formula exactly to counteract noise.
But I mean, the tool has to be sort of compatible with the tools that you're doing, right?
Yeah, exactly. But they also looked at like Clifford twirls, which is basically randomized benchmarking, and tensor products of Clifford twirls, which is basically what Steve has been doing for the last couple of years, the Pauli randomized benchmarking. And for me, this was like very surprising and a very smart idea, because you don't actually have to know the noise. You can learn it in advance and invert it still. And then there's been extensions to fermions, which
Richard, I mean, one thing, I mean, the Steve's scheme has like a big drawback, which comes from randomized benchmarking. I mean, he has to assume left noise.
Yes.
Because I mean, if the noise acts on the state first, you're screwed anyway.
Yes.
And I mean, why this is like an innocent assumption in randomized benchmarking, because there, I mean, like the right noise once goes into the spam, it's a highly non-innocent assumption in like for the shadow calibration.
Like half robust.
Yeah. But you're telling me that kind of if the state is affected by noise, then we can't remove that?
Yes, exactly.
Yeah, but I would say that's kind of
no, but I mean also like I mean if the noise acts like in front of the measurement, yeah, like the measurement like there's a model that which is like action of some noise, then the measurement, then some noise, then you can also just remove part of the noise. And like like this left independent noise assumption is like a highly non-trivial assumption, which can be removed in randomized benchmarking, but I mean here it can never be removed. So I mean,
yes.
So it's unclear how realistic this is in any schemes and what you can do about it.
I'm interested. I wasn't aware of this subtlety. Let's talk more later. And
but this can be fixed, in fact. But we can discuss this later.
And yeah, there's Bayesian interpretations, which I kind of like because I like probability theory. IBM came up with a way of how to bias kind of the sampling distribution of Paulis. Like the way I explained it in the single qubit formalism is kind of you sample each of your single qubit basis measurements uniformly at random. It shouldn't come as a surprise that in general this is a bad idea, because if you want to do quantum chemistry and the Jordan-Wigner transformation, then you hardly ever see Y terms, and so you should never estimate Pauli Y. And so kind of they found a clever way of like kind of how to adjust the distribution of like sampling each single qubit Pauli measurement in order to get superior performance. And last but not least, kind of this is something that I kind of like, is a couple of weeks ago, Robert, John, and me uploaded a paper on the archive where we kind of de-randomized the entire procedure. There's a standard technique in classical computer science that allows you to take a probabilistic argument from the probabilistic method and squeeze out the randomness entirely to come up with a deterministic strategy that works just as well. And it shouldn't come as a surprise. I'm happy to talk more about this later, but Jens, that's also my answer to your question. Whether you should like do multiple measurement repetitions of the same basis measurements or do something else, run de-randomization. It will give you a good strategy.
I see. Thanks. I should have thought of this myself. Yeah, thanks.
Okay. So yeah.
Is this a constant factor improvement, or is this that you have in this plot?
Kind of here, yeah, that's kind of like one particular example that kind of where you actually try to like kind of do VQE for like a small molecule, BeH2. And kind of, as you can see, kind of the original classical shadow orange is actually not that good. And the IBM gang with the biased shadows kind of made it much better to this green line. And de-randomization, this standard procedure actually gets you down to the blue line. And in the examples we did, it's kind of always a constant improvement of 1 to 2 orders of magnitude.
Okay, thanks.
So don't expect outlandish performance gains, but it's an efficient preprocessing algorithm that kind of saves you 1 to 2 orders of magnitude, which is a constant, yes. Okay, with that, I see that kind of we're anyway running out of time already. Should I continue or should we wrap up here?
No, I think it would be good to continue a bit.
Yeah, I'm sorry for I should have been much quicker. Okay,
you're still about to make your connection to learnability punchline.
Yes, but maybe not exactly, and some unpublished results. Exactly. Let's now quickly just wrap up by like motivating a transition to machine learning. I think it's very fruitful of viewing classical shadows really as an efficient and reliable quantum to classical converter. Like you have an underlying state, and this formalism tells you like how to efficiently extract information about the system. We used it to predict many observables. And Vqe is kind of like also, if you just view it classically, it's kind of like a kernel method. You start with a couple of parameters that parameterize the circuit, and that's effectively a map in a very high dimensional space. You map the parameters to the state that is kind of generated by this circuit. And then afterwards, you form a quadratic function with a Hamiltonian to get a number. You should view that as a particular kernel method, actually. And an obvious question is, can we get that's actually work in progress that we plan to like submit soonish, is kind of learn how to predict ground state properties. So kind of we hypothetically envision a sufficiently nice parameterized family of Hamiltonian, where kind of like each Hamiltonian is parameterized by an n-dimensional classical input. Like think single qubit.
Can you like repeat the last couple of sentences, because we had some audio problems apparently.
Oh yeah.
So like from the last slide. Thank you.
Kind of think of classical shadows as quantum to classical converter, and think of Vqe as a particular instance of a kernel method. You kind of start with classical parameters, you go in an outlandishly large space, you compute a function, and then you use that to like do some stochastic optimization. And we saw that classical shadows can give you quite substantial performance gains for Vqe. Now the question is, can you get something similar for more sophisticated machine learning procedures, like not just Vqe? And the problem we want to look at is the problem of predicting ground state properties. Like you assume that you have like a sufficiently nice family of parameterized Hamiltonians, where kind of X is just a classical input that characterizes your Hamiltonian. Like think of a Heisenberg Hamiltonian, where like the X are like kind of all the couplings. But the parameterization need not to be known. It just has to be like nice spectral gap and like sufficiently smooth. And then each Hamiltonian comes with a ground state. And the question we ask ourselves, the learning question is, can we kind of like learn how to predict ground state properties, like kind of observables of ground states associated with Hamiltonians that we haven't seen yet? And the kind of training data we assume is quantum mechanical. That's kind of the twist, because classically this is a difficult problem, but we kind of assume that we have nice friends in like experimental material science labs, for instance, who can like sample an input parameter at random and kind of prepare the ground state associated to the Hamiltonian also by like cooling it down, and perform a classical shadows measurement, but the simple one, the one with random single qubit instances. So we kind of assume that the training data we have access to is the classical input X associated with a classical shadow single shot of the associated ground state. And here you really need an experimental friend in order to do that. This is something you can't generally do just purely classical. And the ansatz, and then now we want to like kind of generalize and predict features of ground states that we haven't seen yet. And the ansatz is, as I said, you train a classical kernel method with classical shadows. And so in the learning phase, we really ask our experimental friend to sample random control parameters, prepare the associated ground states, and construct the classical shadow for us, which means single shot measurement. And in the prediction phase, we kind of just use, for theory purposes, a rather simple Fourier type kernel function in order to kind of convolve all the classical shadows we've seen in order to get an approximation of the ground state that we haven't seen yet. That's kind of just a kernel trick with a truncated L2 Dirichlet kernel. Kind of just this, a very simple linear learning model. Okay, and this kind of gives us an efficient representation for future ground state Hamiltonians. And then this hopefully allows us to compute the observables, and then we kind of have a prediction. Okay, and now here's the thing that kind of surprised me. You can actually prove that this works. And if you're interested in kind of small average case prediction error, kind of like you just want to like kind of have a small prediction error averaged over all possible inputs, which is kind of a standard assumption in machine learning, then the number of training data you need is not that large. It's quasi-polynomial in n, which is the number of input parameters, not the number of qubits. And so again, we're kind of in a situation where the number of qubits, the size of your many-body system doesn't matter at all. All that matters is kind of the number of parameters in your Hamiltonian. Okay, and of course, there's like some assumptions in order to make that. For instance, we need that the Hamiltonian family has constant spectral gap. But the proof technique is actually not that difficult. It kind of involves a bit of Fourier analysis from signal processing. This is why we use kind of a Fourier type kernel to make sure that truncation and everything works. And the other ingredient is really just rapid convergence of classical shadows, which kind of gives you a rigorous explanation why you can replace the ground states that you haven't seen by classical shadows.
And with gap, you mean like a gap independent of the system size that surely enters to have like a robust ground state property.
Exactly. Yes.
But does it enter elsewhere as well, or is it just basically just to make sure that you get a robust result?
No, it's important to like tell you that you can actually do a truncation.
Okay.
This is a Fourier type kernel, but we truncate it, and so it's like in signal processing where you need band limited signals.
I see. I mean, that's
and like constant spectral gap is one way to ensure that your learning function is band limited.
Yeah, thanks.
And empirically, like for the systems, we could do that. We tried it for a Heisenberg model. Robert set that up, and it actually kind of works quite nicely. The system sizes are not that large because it's kind of a 2D system. It's not so easy to like simulate it, but you can see that kind of the system size actually doesn't affect the prediction error. What really matters is the size of the training data. And for us, that was quite surprising, because if you didn't have an experimental friend who kind of prepares the classical shadows for you, then these kinds of problems are hard classically. So kind of something is going on. And what we believe, and I think we have good evidence for that, is that classical data obtained from quantum experiments can be surprisingly empowering, and then can do things that classical procedures can't.
I mean, what do you mean by hard? I mean, in the sense that, I mean, these kind of QMA hards Hamiltonians, I mean, they're all not gapped, right? They are gapless Hamiltonians. So where's the hard part coming in on the quantum side?
Even with spectral gap, the hard part comes in that kind of you can also choose the observable to be like a sum of local terms.
I see.
And then you can like kind of do weird things and like to encode rectilinear 3-set or something.
Okay. Yeah.
By like kind of just checking like kind of or yeah, exactly. That's how we do. We kind of use the fact that we are interested in observables and rather accurately to kind of encode 3-set.
Okay. Cool.
Okay.
Question on the kernel.
Yes.
So did you need to use this Fourier type kernel to make the proof work, or did you just like set out with this kernel and then make the proof work?
No, the kernel is horrible. We just used it because you can do theory for it. Kind of like it's a highly theoretically motivated kernel that is kind of decomposed in 3 natural steps that allow you to prove this theorem. But in practice, you should use other kernel techniques. Like I think what worked best empirically was gradient boosting.
Very good.
But this is really just in order to get this theorem with a quasi-polynomial scaling and training data size.
Okay, but I mean, you would in theory expect that for other types of kernels or like more common ones, you could also prove such a theorem, but it's not yet clear how.
Yeah, exactly. It's kind of like this was the kernel where we were strong enough to prove something.
Okay, cool.
Okay, and that's kind of like almost the last part. And this is like kind of another paper that we kind of uploaded in January, where we kind of ask ourselves, like kind of, we were a bit surprised of how powerful this method actually seems to be. Kind of like use a quantum device to generate data, use classical shadows to use it efficiently, and then use a classical machine learning procedure. And so we kind of try to contrast this kind of way, which I would call like classical machine learning with quantum data, which kind of involves kind of only classical updates and a physical experiment that always has to be concluded with a measurement that kind of gives you the classical shadow, for instance, and then you adaptively go on. And let's contrast that with a hypothetical, fully full-scale quantum machine learning protocol that runs on a future quantum computer that has coherent access to the training data. And what kind of this model on the right could, for instance, do, it could kind of entangle the input for your experiment, which is the black box, with some quantum memory, and then kind of use coherent access to this training information in order to come up with a more powerful strategy. So kind of on the left-hand side, we kind of, this is like kind of a cartoon for every machine learning procedure that might be adaptive, but you generate training data sequentially and without entanglement between them. And this involves, in particular, the scenario I explained before, but it also includes all the near-term machine learning approaches we have today. Because today we also use sequential access to data in order to drive them. And on the right-hand side is really kind of the most powerful quantum machine learning procedure you could envision. And we wanted to get some idea of how the two compare. And perhaps surprisingly, in order to compare, we need to kind of come up with a benchmark or with an objective. And we wanted to use, again, kind of function prediction as kind of the learning problem where we let the two race against each other. And so the question is, again, you have a classical input like a parameterization of Hamiltonian, and you want to estimate a linear function, which is essentially an observable that acts on a physical process, on a quantum mechanical process that is kind of depending on the input. Like learning ground states is one example of such a learning problem. More general physical experiments like chemical reactions can also be phrased in this formalism, or closer to home, every quantum computation can be written in this form. And so we considered kind of this was our learning goal. You have a reasonable physical function like this that you want to learn. And now how do the two different machines, one kind of hybrid machine learning approach and one fully quantum approach compare? And perhaps surprisingly, if you again only focused on average case prediction error, like that your prediction error is small, averaged over all possible inputs, then we prove that there cannot be a large separation between quantum and classical training data size in terms of sample complexity, in terms of the number of measurements we need in order to get accurate prediction. And so this is a statement in terms of sample complexity, in terms of training data size. And what it effectively tells you is, think of a hypothetical, regardless of what the most powerful general quantum machine learning procedure required as training data, you can also come up with a classical machine learning procedure that kind of has a training data size that is comparable. So in terms of sample complexity and average case prediction error, there can't be a large separation. There can, however, be large separations in terms of computational runtime. This is really just about training data size. And so if you want to get kind of a really exponential separation, a quantum speed up, if it's a wish, for a future fully quantum machine learning procedure, then you can go to worst case prediction error, which is much more rigid, where you actually demand that you accurately approximate the function for each possible input, and then exponential separation becomes possible.
But two obvious questions at this point. I mean, so the second is not only that it's possible, but there are examples where this exponential separation is realized. So that's a bit similar to the work by Ryan and Jean-Pierre, Dominic, and myself. And then the other obvious question is to what extent is the linear function setting generic? Do you have some intuition? To what extent?
What do you mean linear function setting?
No, I mean your goal. I mean the goal is to learn to predict expectation values of observers, which is of course very suited to your framework. But can you also think of higher order polynomials that are copies of quantum states or something?
I think so. That's a very good point. We didn't think too much about that yet. For us, this was kind of a natural setting, but you're right. Maybe we should move on to polynomials and try to do something similar. And for your first question and comment, exactly, it's kind of very similar. And kind of the problem we consider actually is very easy, where you see an exponential separation. It's simply epsilon accurately predict all Pauli observables. That's kind of the problem that does the gap. Mm-hmm. Because you can use shadow tomography ideas like Aronson invented them originally, and use kind of coherent access to multiple state copies to kind of solve this question very efficiently. Whereas if you only have access to classical shadows are in a way optimal, and they scale exponentially in the weight. And if you want to predict all poly observables, the weight is exponentially large, and so you're basically screwed. So
Okay.
kind of this is the proof of like the exponential separation here.
Okay, wonderful. Yeah, okay, get it. Wonderful. Very nice.
Okay, and with that, I think I'm wrapping up. Thanks for your attention. Thanks for all the great questions. I also learned a lot. And let me stop a bit selfishly with my not so hidden agenda, because I want to put Linz on the table for you. Austria is kind of still, this is kind of where I am right now. And I think it would be nice if you put it on your map, and you're also very welcome to visit. If you want to visit, I put like kind of a roadmap here. It's very easy. You always go south, and it takes you 6.5 hours. And there might also be intellectual reasons to do that. Kind of, I would argue that Austria is still a rather strong quantum nation. And here in Linz at JKU, Johannes Kepler University, we kind of focus on quantum computer science, which is a bit complementary to what other Austrian groups are doing, like the Innsbruck gang and also the people in Vienna. And so, for instance, like there's me, and I like to use randomness in order to kind of come up with algorithms or procedures that kind of come with rigorous guarantees and theory support that kind of make near-term quantum devices more tractable. But I also have like, we also have like a really cool real computer science team led by Robert Wille, and they are really design automation specialists. They kind of focus on that kind of the large in-between, between like single qubit gates and like a fully functioning quantum processor. And they're also really good at simulating quantum mechanical systems by using redundancy. So I think there's also like intellectual appeal in Linz. And yeah, thank you very much for your attention. And yeah, come visit us either at the webpage or once the borders open again in person.
Wonderful. Thanks. Clap, clap, clap. Thanks for this wonderfully inspiring talk. And I mean, the many questions speak from themselves. I mean, that's clearly hitting a nerve here. By the way, 2 days ago, I was like 50 kilometers away from Linz. For that
What, really?
Yeah. In close to Passau.
Okay.
Yeah. Anyway. Yes, so we had lots of questions. I'm sure there's more.
Yeah, I have a question. So it's kind of like a definitions question, something that's been confusing me for a while. So there's this kind of old framework of Scott Aronson of PAC state learning, where you imagine that what you're given is you're given expectation values from a bunch of 2-outcome POVMs selected from some distribution over like some subset of 2-outcome POVMs. And you want to like efficiently learn a classical representation of a state that allows you to predict sufficiently accurately the expectation values of like future 2-outcome POVMs drawn from the same distribution from the same set. And then I understood kind of shadow tomography as being a restriction of this learning framework, but I'm struggling to put the two things together. In other words, the way that I understand it in your framework, what you're given is not a whole bunch of, you also learn a classical representation of a state, which allows you to predict expectation values with respect to measurements from some set. But in order to get your classical shadow, what you really need is outcomes of measurements in the computational basis. You don't get expectation values of operators, you get really single shot outcomes. So do your classical shadow learning algorithms here give you learning algorithms for sets of states in Scott's state learning framework? Or I don't understand how to like put these two things together.
Let me, I'm a bit shaky on like the first example you gave, to be honest, but let me kind of like try to like motivate the results I talked about from a different perspective, starting from Aronson's shadow tomography.
Yeah.
Kind of when Aronson introduced shadow tomography, it was a learning problem where you're interested in predicting the outcome probabilities of very many 2-outcome measurements.
Exactly.
Accurately and for any state on a d-dimensional Hilbert space. And the rules of the game are as follows. You can use all the quantum power you can imagine. In particular, you can use coherent access in a quantum memory of different state copies. But kind of the rule of the game is make the number of state copies you need to query as small as possible.
Okay.
And kind of what Scott Aronson showed, and this is kind of really remarkable, is that if you have access to a quantum memory where you can kind of coherently store all your states, and then you do like complicated entangling circuits on all of them and gentle measurements, essentially, you can predict, kind of accurately estimate all these outcome probabilities with a number of state copies in your measurement, in your memory, that is only polylogarithmically in the number of two outcome measurements you want to predict, and polylogarithmically in the Hilbert space dimension. Okay.
Cool.
So that's kind of how I view shadow tomography. And then what we kind of did is the classical shadows are a constructive protocol where you kind of drop the quantum memory. Where you say, okay, now let's wrap up the difficulty a bit. What if we only have access to like independent copies of the state?
Okay, cool, thanks. I understand. I mean, there's lots of different games somehow, and I guess I never really understood what the rules of the shadow tomography game were, but now I understand. That makes a lot of sense. Thanks. Yeah. Cool.
And may I go next?
Yeah.
So lately I've been, last months I've been working a lot with like Fisher information, and also the question of how you can compute that in like this NISQ context. And one way to do so is to take like the fidelity of your state with like a slightly perturbed state. And I looked at your paper, and I think there's an example of calculating fidelity with respect to some fixed state that has an efficient classical representation. But can I also use this shadow formalism to take the fidelity, and best would be like the Burris fidelity between mixed states, between two states. So I mean, I can imagine that you can just like take the two estimators. If they're independent, you get like also some kind of estimate of the fidelity. But I mean, does this work well? Did you look at this?
We didn't look at that yet. Burris fidelity as kind of standard fidelity is a bit scary. If it's a polynomial, I think it's a bit more kind of trace row 1, row 2 is less scary than Ullmann fidelity of the two, I would say. But like kind of what you can do with classical shadows is you can kind of approximate polynomials also rather efficiently. And perhaps surprisingly, like the number of samples you need for a degree P polynomial is only linear in P. It is not exponential in P. The problem is kind of, and what I want to say, and now, are we still recording, Mark? Okay, I don't know if I should say that now, but statistically, you are in trouble.
We are recording. We are not recording the discussion. I mean, exactly. Even if we are recording this, when we put it out at some point, or
I think what you want to do, Johannes, is you maybe want to take classical shadows to get an idea about like kind of what the other state close by should be or behave, and then kind of use the same data to kind of estimate the cross correlation. And that's kind of statistically a no-go. Kind of like you have to be a bit careful. Like what classical shadows tell you is you can kind of compute many pure state fidelities, but a rule of the game is that kind of you have to fix these fidelities before you do the experiment. Kind of the fidelities that the states or the observables you're interested in cannot depend on the data you already took.
But Richard, like with the I mean, is this like with the scheme, like with doing like 2 times shadow estimation, is this kind of like Andreas, like similar to Andreas comparing of like quantum devices, where they do like a cross entropy, basically by estimating like from the both centers? I mean, this is kind of like what you're supposing.
Yeah, exactly. All I'm saying is you have to be careful by like kind of using the data to get an idea about where you should go, and then using the same data again.
Okay. Yeah, okay. I was actually not thinking about reusing the same data. It's just like, I mean, you dial in one parameter value, take a classical shadow, then you dial in the next parameter value, take a different shadow, and then use those 2 shadows to hopefully compute the fidelity.
Yeah, I don't see obvious problems actually, but I also am not aware of any result in that direction.
Okay.
Sounds like a cool problem.
Yeah, good. I guess it will work, but it's just like, I mean, also estimating metric square roots is yeah, as you said, it's kind of a little bit scary. Okay. Yeah, good. Thanks for the answer.
Maybe I can ask one more question. So you have this de-randomization procedure, and I'm a little bit confused how this makes things better. At least like naively, the way I understood de-randomization is that you sacrifice randomness for a kind of polynomial slowdown in runtime. This was like my naive understanding of de-randomization. And in your case, it seems that when you de-randomize, you get an improvement in the number of measurements that you have to do. Can you just like give a little bit of intuition how this works?
Sure. Let me start with a high-level intuition and then like explaining a problem that is not classical shadows, but hopefully conveys the intuition.
Yeah.
Like first is like kind of a philosophical or like kind of an opinion. And I think like kind of randomized measurements are cool, not because they do the right thing, but because they never do the wrong thing. Kind of if you do randomized measurements, then no matter the state and kind of no matter the fine structure of the things you care about, on average, over your selection of randomized measurements, you will not do too poorly. Okay? And then like there's an additional step involved in randomized measurements that is kind of the tricky part where you have to kind of show that a concrete randomized measurement instance kind of will behave comparably to what you expect.